we're given this biochemical signaling molecule IP3 diffuses from one cell to another, blah, 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 blah. And we have these differential, right? So called the X1 be the concentration of IP3 in cell 1, X2 is concentration in cell 2, respectively. The dynamics are given by dx1 dt equals negative 2x1 plus 2x2, and dx2 dt equals, I feel like I got that. No, that's right. Equals 2x1 minus 2x2. So I suppose it is reasonable to have a system like this where essentially the amount of stuff going from x1 to x2 and the stuff from x2 to x1 is like the same, right? You're losing 2x1 from x1, it's going into x2, and you're losing 2x2 from x2, and it's going into x1. So it's not an unreasonable system to have. Let me make this a little bit smaller here. There we go. Oops. Come back, chat. Okay. So first question of this is the eigenvalues and eigenvectors of the matrix are given by the following. So you have lambda 1 equal to 0. V1 is the eigenvector 1, 1. And lambda 2 is equal to, what did we get here? Negative 4. And V2 is 1, negative 1. And the matrix that they didn't write down, the matrix is this matrix, negative 2, 2, 2, negative 2. And that's our matrix that we got these eigenvalues and eigenvectors from. What is the general solution for the system of the differential equations? Well, that's super not terrible, right? If they give you the eigenvalues and eigenvectors, we know the solution to the system of equations. The solution, the general solution to the system of equations is just x of t, y of t equal to c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. In this case, so that's going to be x of t, y of t equal to c1 e to the lambda 1t. Well, lambda 1 is 0. E to the 0 is 1. So e to the lambda t part is just going to give you is a 1. And then v1 is 1, 1. And then you're going to get c2 e to the negative 4t times v2, which is 1, negative 1. Okay. So then they also asked us to describe what happens to x1 and x2 as t goes to infinity. So can anybody tell me, as t goes to infinity, what happens to e to the negative 4t? Where does it go to? Right, it goes to 0. So as t goes to infinity, xy is going to go to, well, just this part, because this part's going to go away. So we're going to get c1 times 1, 1. That's it. So x1 is going to c1, x2 is going to c1. And there's lots of ways you could express that. Okay. So then they want us to graph the eigenvectors in the x1, x2 plane and indicate the flow along the directions of the eigenvectors and sketch. Okay, well, let's do the eigenvector part first. So the eigenvectors are 1, 1 for lambda equals 0. So that means over 1 and up 1. So it's the line y equals x. Right? There's your eigenvector 1, 1, or your eigenline, really, right? It's the eigen. So instead of graph the eigenvectors, I feel like they really mean graph the eigenline. Because right, if you're graphing the eigenvector 1, 1 would be like that, which is not really what they mean. I don't think. So I would graph it like that. Although maybe let me give you two options. So I'm going to do it graphing the eigenlines and then also graphing it just as eigenvectors. So here's the eigenline for lambda 1 equals 0. And if I was actually graphing the vectors along the eigenline, well, lambda 1 equals 0, meaning you're not going inwards or outwards. There's actually no direction of travel when your eigenvalue is 0. So you would just have all these zero vectors, which would be kind of super lame. But I really feel like he meant you to do it this way. Whatever. The other eigenvalue is -4, and it's associated with the eigenvector -1, 1. Or sorry, 1, -1. Same difference, really. So we're going over 1 and down 1. And since the eigenvalue is negative, all the eigenvectors are pointing inwards. So we're pointing that way, we're pointing that way, right? We're pointing that way. If I was actually drawing these vectors, I'd have like a vector there, a vector there, a vector there. They're all pointing exactly in the direction of the line y equals -x. Okay. So here's the thing. Well, in fact, what's interesting about this eigenvalue being 0 situation is that there is like nothing's pushing us this way or this way. All of the direction of travel is straight that way or straight that way. So that in fact, if you, no matter where you start, right? If you start, let's say we started over here at the point, I don't know, -1, -2, negative. Let's say we started at the point -3, 1. We're going to point in a direction exactly parallel to that eigenvector or that eigenline. What's also interesting about this situation is you actually have multiple equilibria. In fact, anything on this line here is an equilibrium point, right? Because 0, 0 is certainly an equilibrium, but so is 1, 1, right? If you plug in 1 for x1 and 1 for x2, you get -2 + 2, which is 0. If you plug in 1 for x1 and 1 for x2, you get 2 - 2, which is 0. So 1, 1 is also an equilibrium. 3, 3 is also an equilibrium. Anything that's on the line y equals x is also an equilibrium. Anything that's on the eigenvector or the eigenline associated with lambda equals 0 is also an equilibrium. Interesting. So then they also ask us to graph the trajectory for the initial condition x1 equal to 0, y and x2, sorry, x1 equal to 2 and x2 equal to 0. So if we go over, right, 1, that's like 1. So if we start there, we're going to go exactly parallel to that. So we're going to go exactly that way. And we're exactly pointing at the point 1, 1. If you start at 2, 0 and you go up left 1 and up 1, you're going to end up at the point 1, 1, which is on the eigenline. Okay, I think that's really all there is to sketch for the trajectory. And then using your sketch from chart D, draw x1 of t and x2 of t for the initial condition. So they want you to then take, so I'm going to graph x versus t, and I'm going to graph y versus t. Okay, so I'm starting at time equals 0, and at time equals 0, x is equal to 2. Okay, now, as time goes on, forever and ever and ever and ever, what is x getting closer and closer and closer to? Oh, it's getting closer and closer and closer to 1. It's never actually getting to 1. We have this asymptotic behavior. Again, if you look back at your general solution, I know this goes to 0, but so I will point out that for our initial condition 2, 0, if your initial condition is x is 2 and y is 0, your coefficients here are 1 and 1. C1 is equal to 1 and C2 is equal to 1. You don't have to know that to solve this part of the problem, but it's worth mentioning because it's easy to see. Right, 1 times 1 plus 1 times 1 is 2. 1 times 1 plus 1 times -1 is 0. Oh yeah, those are solutions. So if you look at this, basically what's happening is that x is equal to C1 times 1 plus C2 times e to the -4t. So as time goes on, right, and specifically it's 1 plus e to the -4t. So at time equals 0, x1 starts at x1 starts at 2, right? T equals 0, you get 1 plus 1, which is 2. And then as time goes on and on and on and on, we're going to exponentially decay and get closer and closer and closer to 1. You don't have to know the particular solution to see that, but it's not bad to also see that. So we know that we're starting at x equals 2, we're getting closer and closer to 1. And then for y, and this is 1, right? Same sort of thing is going to happen, except that y is starting at 0, and y is getting asymptotically closer and closer to 1, like that. And that's all of question 1. Are there questions about question 1? Well, if you think of a question, you can always welcome to ask it later. Let's look at question 2. So question two, I hope was a super straight shot for everyone. Like I feel like question 2 was meant to be kind of very straightforward. So let's go ahead. Let's just actually talk through it because I don't think there's really anything for me to write. So let me share it with you just in case you don't remember. So here is question 2. Oops, whoa, that's not question 2. I just clicked on a different file. Okay, here's question 2. So for each schematic phase portrait corresponding to a system of 2 linear differential equations, 1, classify the steady state as 0, 0, meaning as a stable node, unstable node, etc. And 2, describe the eigenvalues of the system in each case. All right, great. So let's look at A. So everything is pointing inwards, so it's stable. It's not a spiral, so it's got to be a stable node. Excuse me, since it's a stable node, we know the eigenvalues are both negative. And again, if you have questions or comments, please feel free to chime in. For whoever just came in, we're just going over the short test that you guys had earlier today. So for B here, it's clearly a spiral, and it's clearly an inward spiral. So that's a stable spiral. And we know for a stable spiral, the eigenvalues are complex, and the real part has to be negative. For C, we have a saddle. Saddles, the eigenvalues are both real, and they're opposite signs. One is positive, one's negative. Here we have another spiral, but it's an outward spiral, right? We're spiraling away from the origin. So that's going to be an unstable spiral, where the eigenvalues are still complex, and the real parts are positive. Here we have something that's unstable as well, because we're shooting out from it. So it's, but it's not an unstable spiral, it's an unstable node. So the eigenvalues are both positive real numbers. And finally here, we have a spiral, but it's not spiraling in or out. So that's what we call the center or a neutral spiral. Both the eigenvalues are complex. Specifically, the eigenvalues are purely imaginary, right? The real part of those eigenvalues is 0. I feel like we've talked about that a lot. So I hope everyone aced that one, because I definitely feel like it was meant to be a question where everyone could pretty straightforwardly answer it. Let's see here. Yeah. I'm not surprised it was worth less points, because it was he probably meant for it to be a little bit easier. This last question was a little bit challenging, I'm not going to lie. I definitely asked one like this on the practice test, but I did not ask the part about where you have r equals 7. So what on earth we were supposed to put r? So yeah, we'll get there, Zach, for sure. So he did talk about something like this in the notes from the last class, where you have the extended linear system, which is definitely what I went and looked back at to figure out how to answer it. Yeah, we'll do it right now. And this also definitely pertains to, I believe this pertains to the question that Shanna asked about part B, because part B on your, what's it called, your discussion worksheet, right? There's definitely a differential equation where you have a plus a number in it, right? Which is, again, different. Now, there's kind of two things here. The actual solution, once you figure out what you're doing, is really, really straightforward. The derivation of the solution, which is in his notes from the last class, is a little bit complicated. I wrote it all down, and I was like, oh, you don't really need to actually have to write this all down. You just have to like kind of know what happens. Yeah, I believe it does have to do with the x. I believe it's called x tilde, the x with the squiggly line. Yeah. So let's go ahead and look at this problem. And I've got my notes here so I don't screw it up. Okay. So let's write things down. So first we have to draw the schematic, which hopefully wasn't too terrible. Just to see what's going in and what's going out. And it's really a good idea if you're drawing something like this to label what's what so you don't forget what's what. Yeah, the thing, yeah, Kavina, right? The whole thing ends up being like you have to find this other like vector, but the matrix you deal with essentially ends up being the same. Let's take so let's go ahead and do it. So got my system here, right? And this is X1, which is the drug in the blood, right? X1 is the drug in the blood. So drug in blood. And this one here, X2, is the drug in the soft tissue. Okay, so let's see what we've got here. The rate at which the drug is absorbed from the blood and excreted in the urine. So that means it's going from the blood out the body. That's going to be 1x1. The rate at which the drug is absorbed from the blood by the tissue, so that's from the blood to the tissue. That's going to be 5x1. And then the rate at which the drug is reabsorbed from the tissue to the blood is 1x2. The rate of drug lost from the tissue through enzymatic degradation is also 1x2. And finally, and this is kind of the weird part, the rate of influx of drug into the blood through the IV drip is R. So we're coming in with an R. Great. So we're supposed to draw arrows, thoroughly label them to indicate the rates of change. Yeah, we've got it. Great. Determine the system of differential equations. Okay, that part also shouldn't be too terrible. So you've got dx1 dt. So what's happening with x1? Well, we're losing 1x1 and we're losing 5x1. So we're losing 6x1. So we have the negative 6x1. We're gaining 1x2. And we're also gaining r. All right. For dx2 dt, we are, let's see, x1, we're gaining 5x1. And we are losing 1x2 and another x2, so we're losing 2x2. Okay, so that's your system of equations. And then they tell you if r equals 0, then the general solution is, what have I got here? So x1, x2 is equal to c1 e to the negative t times 1, the vector 1, 5, plus c2 e to the negative 7t times the vector 1, negative 1. Great. So then they ask us, what's the steady state when r equals 7? So let me point out, the steady state is just another name for the equilibrium. So when r is 0, what's the equilibrium? It's a real common answer. You guys know, you've seen it 100 times. If we don't have an r here, yeah, right, exactly. x1 and x2 just have both have to be 0. Because again, when you're finding the steady state, aka the equilibrium, you're setting each differential equation equal to 0, because you want to get to the place where x1 and x2 are not changing, where things are steady, where the rate of change is 0. So now we're going to do the same thing, except we're going to set r equal to 7. I think I can do away with this picture here. So all we're going to do is we're say, okay, I'm going to set r equal to 7, because that's the number they gave us. And then we're going to set each of these equations equal to 0. So I'm going to have negative 6x1 plus 1x2 plus 7 equal to 0. And let's use a different color for the other equation. We're going to have 5x1 minus 2x2 equal to 0. Okay, here's the idea. We're going to use this equation that doesn't have the r part in it and solve for one of the variables. And noticing that x2 is all by itself in this first equation, I'm going to solve this one for x2 So I can sub in for that x2 up there. So negative 2x2 equals negative 5x1. x2 equals positive 5 halves of x1. I'm going to go ahead and plug that in for x2 right there. So then I have negative 6x1 plus 5 halves x1 plus 7 equals 0. Excuse me, hiccups. Negative 6 is negative 12 over 2. So negative 12 over 2 x1 plus 5 over 2 x1. I feel like I might have made a mistake in my notes, which is perfectly fine. I just want to double check. Yeah, I did, but that's fine. No big deal. You guys can't see my notes. It's all right. So negative 12x over 2x1 plus 5 over 2x1 equals negative 7. Now these numbers are much nicer than the numbers I got in my notes. Awesome. So then negative 12 halves plus 5 halves is negative 7 halves. x1 equals negative 7. Multiply both sides by negative 2/7, and you're going to get x1 equal to 2. And then, which was funny because I definitely convinced myself that was right. And then when you plug back in x1 equal to 2, you're going to get x2 equal to 5. So that's our new steady state. So instead of being 0, 0, our steady state is x1 is 2, x2 is 5. Definitely works here, right? 5 times 2 is 10, minus 2 times 5 is 10. Definitely works here. Negative 6 times 2 is negative 12, plus 5 is negative 7, plus 7 is 0. So that's our steady state. So now the last question, which is maybe hard, it's not hard to answer, it's hard to know how you get to the answer. But the answer is actually really, really straightforward. You take this vector 2, 5, and you add it to your general solution. So for part D, right, so for r equal to 7, your general solution is x1, x2 equal to all this, c1 e to the negative t times 1, 5, plus c2 e to the negative 7t times 1, 1, plus 2, 5. I'm happy to talk more about this if you would like me to. I don't have to, but if you want me to say more about how we get that, I can do that. But it sounds like you guys don't want me to, which is perfectly fine.
Like for the last part, like as you wrote in a combined form, I wrote like separately for x1 and x2. Is that right?
That would also be fine. Although, so you could totally write, you could totally write the last part as like the answer for part D. You could totally write your answers. Yes, you could write it as x1 equals c1 e to the negative t times 1 plus c2 e to the negative 7t times 1 plus, what was it, 2? Yeah, 2. And then x2 would be c1 e to the negative t times 5 plus c2 e to the negative 7t times negative 1 plus 5. That would also be a correct way of writing it.
Thank you.
Yeah. And for the question there, yeah, for D, that is the only answer to the question. That's all they were looking for. You could write it this way, or you could write it this way. It's the same answer, just written differently. Why is this an answer? Well, again, right, if you take, so the whole idea, right, is that the derivative of this should equal, or I really should say, right, the derivative of x1. So if you look at it more this way, right, here's your x1. The derivative of x1 should equal negative 6 times x1 plus 1 times x2 plus 7. And the derivative of x2 should equal 5 times x1 minus 2 times x2 plus 0. So that's why we need this 2 here and this 5 here. So that when we take, So then when we add -6 times x1 plus 1 times x2, we're going to get the 7 canceling, right? If you do a -6 times this plus 1 times this, you're going to get a -12 plus 5, which will be a -7, which will cancel out the plus 7. And then for the second equation, if you do 5x1 minus 2x2, 5 times this minus 2 times this, the constant parts will also cancel out. So it works, right? It's a little bit of so in his notes, the process to figure this out is a little bit dicey. He does this like substitution thing, and then he's like the derivative of this is equal to the derivative of that, so it works out just fine. But in practice, the way we answer a question like this is we just say, okay, take your general solution to the homogeneous system of equations, which is where each thing is equal to 0. So take your solution to where each thing is equal to 0, and then add on your particular solution to where it's not equal to 0. That's how that's working. Are there other questions about this before we take a look at the other thing that was asked about? Okay. Let's look. So I will say this question from worksheet 2 definitely is similar in nature to what we just talked about. So let's go ahead and look at worksheet 2. I feel like I probably shouldn't say like all the things about worksheet 2 because right, it is something you guys are supposed to turn in. But let's go ahead and take a look. So I'm going to look at part A first, actually. So in this model, all right, there's a lot of words to read here, which I don't really want to read. I just kind of want to look at the math. So suppose that the gain, so I'm looking at part A. Suppose that the gain parameter K is 0.5. I don't know what that is yet. That's all right. And that light is turned off. So light off at t equals 0. And so that L is 0. I'm assuming L is the amount of light. The resulting differential equations are the following. dc dt equals -40c minus 20h, d h dt is equal to 10c minus 10h. Right. And I'm assuming, I'm not assuming, I don't really know what C and H are. So, okay, so C stands for the cones, H is the horizontal cell interactions. Okay. So for part A, which we're not going to do, they ask you to do all the things. Right? Find the steady state. Okay, clearly the steady state is 0, 0. And then they ask you to determine the matrix of coefficients, compute the eigenvalues and eigenvectors. I'm not going to do that. So let's just pretend like we know what they are. So here, the general solution, the very general solution would be, C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. I know you guys are all capable of finding the eigenvalues and eigenvectors of this matrix. -40, -20, 10, -10. Hopefully the numbers are not terrible. There's a general solution. Sketch a phase plane diagram. Okay, we're not going to do that. So in the specific solution. Okay. So what I want to talk about is what the other question looks like in terms of what we have here. So suppose again the same gain parameter as K equals 0.5, but now the light is turned on at T equals 0 with a light intensity that corresponds to an L of 6. The resulting differential equations are the following. So the only difference in our differential equations is that now we're adding on a plus 240. And so X, sorry, this is not X, this is C and H. So the only difference in our solution is that now C and H are going to equal still the same exact equation. And this is going to be still the same C1 e to the same eigenvalue times V1 plus C2 e to the same eigenvalue times T times V2. But then we have to add on the vector that is the new steady state. So let's see. So I'm going to set each of these equal to 0. So setting each of these equal to 0, well, setting this one equal to 0, I get C equal to H, right? I get 10C equal to 10H, so C equals H. So then I'm going to plug that in up here. I don't really care which one I plug it into. Let's plug it in, let's replace C with H. So negative 40H minus 20H plus 240 equals 0. So that's negative 60H equals negative 240. So H is going to equal 4. And C is equal to H, so C is also going to equal 4. So what we're going to add on is 4, 4. That's how this system of equations, this general solution to the system of equations is going to be different when you add something on here. So that's kind of always how this, what's it called, this linear extension works. You find the new steady state, you take your old general solution, and you add on the vector that is the steady state. I can say more about this if you want me to. I guess we could, yeah, how do you classify the steady state? I suppose the classification is still the same, right? It still depends on what your eigenvalues are. So if the eigenvalues are both negative, it's a stable, a stable node. If it's a positive, it's an unstable node, and so on and so forth. I don't think there's any difference just because you've changed it a little bit. Yeah. Oh, but he's actually really, you guys are really like doing the thing. Okay, so we just showed the study. I guess we can walk through this a little bit more because there's kind of a lot of pieces. So they ask us to show that the steady state of the system is C equals 4 and H equals 4, which we totally just did, right? That's how you would do that. I didn't realize that's what we were being told they were. So now we're going to define new variables. Okay. So, all right, here is our new system. This is always where things are a little bit kind of weird. And I do want this to make sense for everybody. So we're going to define new variables. So we're going to call it C squiggle or C tilde is equal to C minus 4, and H squiggle is H minus 4. And here's what they want you to know. They want you to know that when you write this, it should be not too hard to see that the derivative of C squiggle is equal to the derivative of C. Right? The derivative, well, if you take the derivative of both sides, the derivative of this is that, and the derivative of C minus 4 is the derivative of C minus 0, because the derivative of 4 is 0. And in a similar way, dH squiggle dt is equal to dH dt. More generally, if two variables differ by a constant, their derivatives are equal to each other. Right? X squared and x squared plus 5 both have 2x as their derivative. Same idea here. Okay. The original variable is shifted by this. So substitute these new variables into the system of differential equations above and simplify to show that they are the following. Okay. So we want to substitute this into the system, which was, there's not enough room. There's never enough room. So the old system was this. It was dc dt equal to negative 40c minus 20h plus 240, and dH dt is equal to 10c minus 10h. Okay, so we're gonna replace, we're gonna substitute in everything that we can. So notably, dc dt, right, that's equal to dc tilde dt. So this is going to become, that's going to be dc tilde dt. And now for c, I'm going to plug in c tilde plus 4. And for h, I'm going to plug in h squiggle plus 4. I think that's what I'm going to do. Yeah. Yeah, that's the way I would think about doing it. So I'm going to have negative 40 times, so again, c is c tilde plus 4 minus 20 times, well, h is equal to h squiggle plus 4. I kind of like saying squiggle better than tilde, I'm not going to lie. Squiggle is more fun to say. And then minus 240. And what should happen is all the constants should cancel out. Let's double check. We're going to get dc squiggle dt equal to negative 40 c squiggle. Negative 40 times 4 is negative 160. And then we're going to get negative 20h squiggle. And negative 20 times 4 is minus 80. And that should have been a plus 240, but I wrote a minus 240 because I wasn't paying attention. Negative 160 minus 180 is negative 240, plus 240 gives you a 0. In the same sort of way, dh dt is equal to dh squiggle dt. And it's going to be 10 times c squiggle plus 4 minus 10 times h squiggle plus 4. And I think you can see here the 40 and the negative 40 will definitely cancel out. So dh squiggle dt is equal to 10c squiggle minus 10h squiggle. So here's what you should notice at this point. These equations are literally the same as these equations without the plus 240. Right? That's really the whole point of doing the substitution, is that you get the same equations with different names of variables, but this system of equations has exactly the same general solution as this system of equations without the 240. So you can be like, oh, we know that this solution that we already found from the previous part of the problem is the solution to that. And then we're going to tack on the, but then we have to, so yeah. So here's what we're going to say. So yeah, this is good. Again, are there any questions about this? Because I'm going to erase some stuff. I guess I'm going to erase on the other side. So here's what we've got. Yeah. So here's what we have. We know that the solution to c of t, h of t, right? We're pretending like we found it. That is c1e to the lambda 1t plus c2e to the lambda 2t. But now I want to find the solution. Well, I also know that the solution for c squiggle, it's c squiggle of t, h squiggle of t, has, and let's see if I can write this the same way. Sorry, I should be careful, right? So this is for, right, this is the solution when your equations don't have the plus 240, right? This is the solution for, there's a lot of things to say here. dc dt equal to negative 40c minus 20h, and dh dt equals 10c minus 10h. Okay, well, this thing I'm writing over here has the same solution because it's the same equations, right? This is equal to the same c1e. Oh, I forgot my vector. Sorry, there we go. This one's equal to the same c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. because it's the solution for dc squiggle equals negative 40c squiggle minus 20h squiggle and dh squiggle dt equals 10c squiggle minus 10h squiggle. Okay, we're getting to the point. The point is, I don't want the solution for c squiggle h squiggle. I want the solution for ch. And here's what we know. We know that c of t is equal to c squiggle plus 4. And h of t is equal to h squiggle of t plus 4. So c of t, h of t as a vector equals c squiggle of t, h squiggle of t as a vector plus 4, 4 as a vector. Well, we know that this is all that. So you take your general solution to the system where everything's equal to 0, where you don't have this dumb plus thing over here, and then you add on your steady state for the new one, and you get that this is the solution to dc dt equal negative 40c minus 20h. Is it really minus 20h? Yeah, okay. Plus 240, and dh dt equals 10c minus 10h. So hopefully this illuminates a little bit more clearly why we're doing what we're doing. Right? We're taking the general solution from the not extended one, right? From what's called the homogeneous system of linear differential equations. Homogeneous because 0, 0 is the solution. And when we add something onto it, all what we just did here shows that all you have to do is take the new steady state and add it onto your old solution. That's it. It's kind of cool, but it definitely takes a little bit of mental gymnastics to kind of wrap your brain around, like, why is this working this way? Are there questions about what we've done here? It's really okay if there are questions. All right, well, I don't really have anything else to say. Hopefully you feel like the test went all right. I know it's always kind of weird to see like the solutions or the answers to the test before you've gotten your results back, because then you're like worried, like, oh, did I do that part right? Or I know I did that part wrong. Try not to worry too much about it, right? The test is over. There's nothing to be done about it now. So I'll see you guys on Monday, where, before anyone leaves, let me take a quick screenshot of the class attendance so I can mark you all present later on. Cool. But yeah, I have office hours right now in 3 minutes, and Monday I imagine we'll be moving on to whatever the next section is. I don't actually know. I'm thinking we're probably gonna start doing some systems of differential equations that are non-linear, meaning there's a little bit more going on, and hopefully we start talking about the null lines, which again, the null lines of a linear system of differential equations are just the lines where it's equal to 0. So, for example, now this is not a good example, but yeah, I think so. Let me actually, I'm going to use these last 3 minutes to say something that I'm pretty sure is going to be coming up later on. Let's say we have this system of equations. Dx dt equals, I'm going to try and make it easy, 2x minus y, and dy dt equals, let's do x plus 3y, sure. Okay, so the null lines you get are what you get when you set each thing equal to 0. So if I set this equal to 0, I get the line y equal to 2x. In my phase plane, y equals 2x, I'm going up 1 over 2. So there's, it's not, I don't really want directions on there because, right? But here's what we know. we know that along this line, since dx dt is equal to 0, there's no left or right. All the arrows are straight up or down. And in a similar way, and usually we want to draw the eigenlines, or sorry, the null lines in different colors. If you set this equal to 0, you're going to get 3y equal to negative x. Y is negative 1/3 x. So we're going. All right, if we get the point like x is negative 3, y is 1. So here is this null line. Sorry, I've been saying eigenlines. And all of the arrows on this are going to go purely right or purely left because the change in y is 0. So everything here is straight up or down, everything here is straight left or right. And what's nice is kind of these things kind of break the phase plane up into sections where, okay, if all the arrows on this are straight up or straight down, all the arrows on this side are either all slightly left or slightly right. All the arrows on this side are either all slightly left or slightly right. It's one or the other. So like if you pick a point, for example, let's say we pick the point 0, 1. Pick the point 0, 1, dx dt is equal to negative 1. So I know we're out of time, and you're welcome to go if you need to go. Dx dt is equal to negative 1. Dy dt is equal to 3. So right here, our arrow is going left and up. More up than left. So I know that in this quadrant of the phase plane diagram, I'm going up and to the left. And then I know that all my arrows here have to be going straight up. And then over here on this side, they're still going to be going up, but they're going to be going up and to the right. And then down here, so this green line is the difference between whether they're going up or down. So here, right, everything's not going up or down. Everything over here is going straight to the right. Everything over here is going straight to the left. How do I know that? Because I know that on this side, things are going left, and this side, things are going right. And then down here, everything would be going, well, now instead of going up, we're going down. So we're going down and to the right. And over here in this quadrant, we're going to be going down and to the left. So the thing about null lines is they kind of help you break up the phase plane into knowing, okay, in this corner of the phase plane, all the arrows are up and right. In this corner, all the arrows are up and left. In this corner, all the arrows are down and left. In this corner, all the arrows are right and left. Sorry, right and down. Apologies. That's what